We welcome Professor Marc Toussaint of the Learning and Intelligence System Lab from the Technical University of Berlin. Marc, please. Thank you, Sarah.
Thanks, Dan, for the introduction. And thanks for the invitation. It's really nice to speak in this seminar. A quick question. You mentioned 50 minutes. Does that include questions, or
No,
is this?
No, it's
Okay.
50 minutes, and then you have about 10 more minutes for questions.
Okay, I wanted to ensure that there is enough time for questions. And if somebody also has some urgent questions during the talk, then just raise your voice. I might notice that. Okay.
Let me just add that if you write questions in the chat, I'll read them.
Yeah, perfect. I'm also happy to share the slides afterwards. Just prepared them last minute if anybody wants them as a reference. Okay, so today I'm going to talk about NLP sampling. NLP is not natural language processing, but a nonlinear mathematical program. So it's more in the direction of optimization, just in case you got confused by NLP. And many math papers, they start right off with, here's the problem that I work on, like in the first sentence. And I decided to do the same thing also for this talk. And just to make clear what this whole talk is about, it's about this here, right? What I call NLP sampling. It is the problem of sampling. Can you see my mouse as well?
Yes.
Oh, that's perfect. It's the problem of sampling from, a distribution, which is defined by an energy function f, subject to constraints, inequality constraints and equality constraints. These are like, high-dimensional functions. So we have a set of inequalities, a set of equalities. The way I wrote this problem here is very close to how you would usually write down a mathematical program, where you write you minimize with respect to x over some cost function f subject to constraints. And I now write, the analogous thing, but the problem is not to find one minimum, but to actually sample from this distribution here. Assumptions are that all of these functions, the constraints and the costs, are differentiable. And just as in optimization, we have access to these functions just pointwise and also their gradients, right? I find this, by the way, here's also a little technical report that I wrote about what I'm also talking about today. I kind of discovered this to be really interesting problem formulation, and relate also very much to the problems that I was hitting and fighting with when I was trying to solve robotics problems. And I kind of found it interesting that I think, but that's an interesting discussion for later, there's actually not so much literature about how you concretely can solve that. And I found it really interesting to try work on that. So the outline for today is that I'm first going to motivate again a bit, actually talking as a roboticist, right? This talk is not so much about robotics, but at least I'll motivate it by the kinds of works that I did in robotics and why I hit upon this problem. And I think it's actually really relevant. And then I'm going to dig a bit more again into the definition of that problem, and also mention that, there are special cases, many existing methods about it, polytope sampling, manifold sampling. Then I'm going to explain you the kind of methods I thought about. These methods are not super original or something. I think they come quite natural. I haven't seen them much discussed before or so. But you'll see, I find it actually really interesting to discuss the spectrum of methods that you can use to do for that. And then also ask how you can actually evaluate the quality of algorithms like that. It's an interesting point. And then just have some interesting discussions how it relates to other things. Okay. So let me go into the first part, motivation. So in previous works, I worked a lot on what is called task and motion planning. Should have written it here fully, but this is task and motion planning. And these are problems that, by the way, relate a lot also to geometric, geometric reasoning, computational geometry, and things like that, which I think maybe some people in the audience know much more about than I do or so. But yeah, I think these problems relate a lot. What you can see here are renderings of the solutions of mathematical programs that formulate the problem. So let me just mention, make clear what I just said in the last sentence, looking at the one here in the bottom left. So what you see here is a little video, the robot doing something. And by the way, the only goal specification was that the block ends up on the green thing. not the only one. Yeah, as well as the kind of options of what kind of things you can interact with. And then you see a solution here, and it looks like a physical simulation. It looks as if I would have taken this from a physical simulator. But actually, this is just a rendering of the solution to a mathematical program. And if you think this looks like physics, this means that I have defined my mathematical program so well that the solution of that program looks like physics, and it respects physics, because I put like physical constraints in the mathematical program. And this is the same thing here for pushing, some examples. And here's also an example for, this one is one that received some attention, like at RSS, a publication where I first applied it to sequential manipulation and tool use. And this is one where we applied on architecture. Okay, so the way I started formulating these problems is as a mathematical program. Let me just briefly explain the structure of that mathematical program. It is over two kinds of variables. So the decision variables of that program are two kinds. The first one are symbolic or discrete decisions. And this is actually a sequence of first order states, first order logic states, I should make clear. So this is a sequence of discrete decisions, and this is a continuous time path. And this is actually the path of the whole scene, not only the robot, but also the objects. And we have some typical costs over the path, like as we have in control theory or so, like we want to minimize accelerations or whatever, some kind of costs of the path. We start at a certain, state in that path. The symbolic decisions, they need to reach a symbolic goal. So these two terms together, they're essentially defined by something like PDDL or Strips rules, some kind of logic description of what is accepted symbolic decisions and what kind of goal you need. So this is more these two, they together define a symbolic kind of the problem. And these last two constraints, they define for every symbolic decision, it implies constraints on how the object might move or how the robot can move, any kind of constraints during that, during a mode of interaction and at the switches of these interactions. Anyway, I don't want to dive into too much details, but the constraints here, these are like really, tedious to also define and program, but eventually these constraints to define correct physics, that everything looks very physical and is correct, but they are defined this in a differentiable manner so that I can use constraint optimization problems. But these discrete decisions, they define the kind of the schedule of how I interact with the objects. Okay, that was enough as a gist of how I formulate these problems. Now, the solvers are pretty involved and also tedious to work with and to develop. Anyway, so there were some papers I had and also some now newer PhD theses that some of my students wrote about these problems. But in essence, the solvers, they all iterate over searching new promising discrete decisions. They're like mixed integer programming, really. You search over some set of discrete decisions, and then whenever you decided on some kind of discrete decisions, which we call the skeleton, it's just the name for that. These discrete decisions, they define the remaining NLP, so these constraints, and this is an NLP, you can analyze it, and then you check if it's feasible or not. If it's not feasible, you try to find like new kinds of discrete decisions, and you just iterate that. Now the caveat though is, well, I should jump right there, that all of these NLPs that you solve as subproblems when you try to solve the overall problems, they're all highly nonlinear and they may have many local optima. And that's the core issue. And that's really a problem, because at some point, if you try to solve an NLP, but you end up in a local optima which turns infeasible, then you might conclude that the whole skeleton is not feasible and then block it from future logic evaluations, and then you're dead. The whole algorithm will never find a solution. So it's really dangerous to, to get trapped in some local optima and believe something is infeasible when actually it is feasible. And that becomes even more worse because very often we use also the NLPs, we decompose them hierarchically. We first solve small subproblems and use those to initialize the larger problem. And same thing, if the subproblems, are found to be infeasible, but it was just, bad luck, local optimum, the whole thing is not robust. Bottom line, in this whole framework, I wish we would have NLP solvers which don't return one solution, but they return all possible solutions, kind of like the diversity of everything, of all possible solutions. And if I would have that, I think my methods, the algorithms for TAMP and for these kind of things would become much more robust, and I could even start speaking about something like probabilistic completeness and so on. Okay? Cool. So that's kind of like the core motivation. And going back to sampling, or the motivation from the robotics point of view, what I'm talking about is a sampling problem. And just briefly, if you look into the sampling now literature, you read things like Markov chain Monte Carlo methods, and they're global samplers. And there is proofs about them being global samplers. But then comes a little but then there is this issue of the mixing times. I hope that some of you know a bit about Markov chain Monte Carlo methods. We're going to use them also here a bit. Or you read papers about Stein variation kind of methods to cover distribution, and you get also basically statements like that they cover the distribution globally and so, or diffusion denoising, or also flow matching models. They're fascinating because they generate a distribution by morphing like a unimodal distribution via a flow into a distribution that globally covers all the modes and everything that you want to cover, which is also surprising that you have a process, a denoising process or flow-like process, which takes a single mode distribution, but then kind of transports into a distribution that covers all possible modes in a guaranteed kind of like manner if you train it the right way. My point is, what's actually the picture? On the one hand, we have NLP solvers being super efficient, but getting trapped in local optima. On the other hand, we have these samplers, and you might have the idea that they solve globally sampling problems. And why do we actually treat them separately anyway? So that's another motivation for this talk, right? Why, or for this whole work? So why do we actually treat sampling and optimization differently anyway? Why is there very different types of textbooks for constraint optimization and other ones for Markov chain Monte Carlo? Shouldn't there be, shouldn't be also taught and treated much more jointly? And I think so. And this is like, this is what I'm trying to do with that work. Okay. Now, let me get into it, the technical part. First, the definition again. So this is my notation for the problem. I didn't really know even what is, what would be a standard notation to formalize that problem, but I hope it's totally clear how I wrote it there. Another notation to formalize the same problem would be to say we define a probability distribution, which is, that part which is defined by the energy or the cost. And then we have these indicators. So these are indicator functions, which means that the probability whenever we violate a constraint is just flat zero. And so this P, the underlying distribution, you should think of it as being flat zero everywhere where it's infeasible, and then, according to the energy within the feasible space. Okay. So we've defined like the problem is sampling from the distribution. And so one maybe first quick question that might come into one's mind is, why don't we just use plain MCMC methods, Markov chain Monte Carlo methods? And a very, obvious answer, there's nothing deep about that, is if you're in an infeasible space, the distribution is flat. And if you use some kind of like methods like Lagrange, which rely on the score function, which means the gradient of the distribution, or also stochastic, Stein variation gradient descent, or anything that relies on gradients. And in a sense, also like a standard MCMC, like Metropolis Hastings methods or something, basically ones, also rely on some kind of like gradient. All of these methods are basically lost in the infeasible space. They don't have a signal. There's nothing, no information in the infeasible space. But from constraint optimization, we know it's insane to not inform the method by the constraint functions themselves. we can evaluate the amount of constraint violation, and we can evaluate the gradient of the constraint function. So we need methods that also in the infeasible space know in which direction to walk towards the infeasible space. Although, and this information is completely hidden in the P. It's just not there. And that's why we want to have methods that really work on this level, that are informed by G and H, not just work on P. Right? Okay. Also, in terms of like discussing the problem setting itself, interestingly, there is, of course, existing literature related to that. So when, for instance, we only would have inequality constraints and the only inequalities would be linear, then a feasible space is a polytope, and there is really interesting methods for sampling within a polytope. And these methods, like some of them, they're called Ball and Dickin walks. I have not, well, I could discuss those as well. They're related to also what I'm investigating, but there is also one which is called Hit and Run. I really like that a lot, and I'm also going to mention it later. The point being is, whatever we come up with, it should include these as special cases as well, right? So it should be at least as clever as Hit and Run. And also, if we would only have equalities, no inequalities, and also no energy in the interior, then this is manifold sample or constraint sampling. So imagine you have some Riemannian manifold, you just want to form a sample uniformly on the manifold. And also for that case, there exist specialized methods like from robotics, there is RTs. You can grow or like rapidly exploring random trees on manifolds, and they sample actually quite well on manifolds. There is also Riemannian manifold MCMC methods that, you know, walk, have random walks on the manifold. And again, the point being is whatever methods we come up with, we should be at least as good or include these ideas in our methods also then for the general case. Okay. But in a sense, I think it's actually not, it's actually not so hard to come up with like a first guess of how you can like generate or have simple like methods to efficiently sample from the problem. And what I'm going to propose, well, I mentioned here already, is it's really not so surprising. It's just a combination of restarting and then what I will call slack downhill and interior MCMC. I'll explain these now 3 steps in a second, and also like, yeah, what kind of methods I considered for these. In order to define these like kind of standard ways to approach this, let me first define the slack vector. I define a slack vector, you know, for any point, if I'm in the infeasible space, I just stack a vector of all the violated inequalities. So this plus bracket here is, nowadays you would say the ReLU. It's just the positive part. So if we are in the feasible space and G is negative, then this is 0. Otherwise, it's just the amount of violation of the inequalities. And this is the amount of violation, the absolute value of the equality constraints. And I just stack them to one vector. Just, you know, the constraint violations, essentially, m plus m prime vector. Now, with that vector, I want to minimize that vector clearly. And so I can take the square of this vector. This is this term here. And I write it like that because I'm really a fan of like Gauss-Newton methods and least squares problems, least squares methods. And this will be one of the methods that we will leverage also to do that. So this least squares problem of minimizing the slack, the constraint violation, is one term in the unconstrained problem that I'm defining, and the other term that I'm defining is just the energy itself, the F itself. And I'm mixing these two a bit unusual. I put like a parameter in front of both of these. You might wonder why in both of these. Simply, the notation makes it simpler, so I can define one case where I set this equal to 0. So when I just cancel this part and only look at that part, then it's pure slack minimization. But if I define that number to be 1 and this one to be really large, like close to infinity, then it is like an infinite barrier energy minimization. So it's like normal cost minimization, energy minimization with an infinite barrier. So these two cases, pure slack or infinite barrier cost minimization, or yeah, this is kind of like the or sampling from the distribution with the infinite barrier energy. that is kind of the limits that I'm interested in. Oh, that's, by the way, P itself, P of X that I defined. Okay. And the obvious approach, I said it already, is to, why don't you devise an algorithm that restarts somehow iteratively, and then goes downhill, slack downhill, until you find a feasible region. And then once you found a feasible region, inside that feasible region, just do some interior MCMC walks to sample a couple of samples. When you have enough, you just restart again. Restart, downhill, interior sampling, restart, downhill, interior sample. Quite generic, right? For the sake of time, I keep the restarting super simple. You can just do uniform restarting or distant restarting. You just restart at points that are far away from the stuff that you've seen previously and sampled previously. I thought this is a great idea, and the evaluations will show it's not, which is an interesting first find. I'll show you later. There is also another thing I tried with restarting, also not great. So the ideas about clever restarting turned out to be actually not so clever. Slack downhill, also no surprise. In constraint optimization, you would, the problem of starting infeasible and then walking down efficiently as possible to a feasible region, that's called phase one optimization in constraint optimization. And this slack downhill that I proposed is one way you could formulate that. There's different ways to formulate phase one optimization. But the reason I like to formulate it like that is because throughout my robotics work, I always love and think it's a good idea to formulate problems as least squares problems and then use Gauss-Newton methods. It's just super efficient to always be able to use Gauss-Newton methods. And so to do slack downhill, a natural thing is to use Gauss-Newton steps to reduce, the least square of the slack. You can also evaluate plane gradient. I did evaluate, but Gauss-Newton was always better. You could have the funny idea to also add noise during the downhill. I evaluate that. Interesting. It didn't hurt, but it also didn't pay off so much. And also it would be natural to actually also use backtracking line searches, just as you do in constraint optimization. So sometimes you make a downhill step, you realize that your constraints actually got worse, and then you do backtracking, like first Wolfe condition. Of course, I tested that as well, but also here it turns out that quite often this didn't pay off so much. So spoiler, Gauss-Newton worked really well, but the Wolfe often was not so helpful. I'll come to that later. So a couple of things turned out in the evaluations to be a bit different than the intuition was. And then methods for interior, like a straightforward method for interior is Lagrange, which means just the gradient of the score function. So you just use that gradient. And then always add some noise. And then this is Metropolis Hastings. I hope you know a bit what Metropolis Hastings is in Markov chain Monte Carlo. This is also a step rejection, but it is a probabilistic step rejection in a Markov chain. Right? If you do Markov chain Monte Carlo and you have a proposed step, if the step doesn't reduce the energy sufficiently, then with some probability you reject the step. And that's called Metropolis Hastings. And also Lagrange, you need to apply Metropolis Hastings to be correct sampling. And instead of just doing gradient steps, you can also use Gauss-Newton steps in the same formalism. And somebody called this, I knew the name, I forgot. Somebody called it Riemannian Lagrange. Also something I evaluated. As a side note, did anybody know that the acceptance rate of Metropolis Hastings is super closely related to the Wolfe condition of backtracking line search? It wasn't clear to me until I really compared it in that little paper and plugged it in. So, but it's kind of like, I found it surprising that this step rejection that Metropolis Hastings does in some case is super closely related to the Wolfe condition when you reject steps in downhill, like in constraint optimization downhill. You can look up in a paper as a side note. And then for interior sampling, I evaluated also other methods that are not typically gradient based, but very different, structurally very different. And one of them that I'm not going to talk about is, I said, RTs on the manifold. But another one I liked a lot is realizing hit and run in the interior space. And I just super briefly also mentioned that. So hit and run is a method for polytope sampling, and it's very efficient for polytope sampling. For instance, if you start here, you have a first interior sample, you sample a random direction, a hit line, I call it the hit line. And then along this hit line, you evaluate where this hit line crosses the polytope boundary, these 2 points, and then you uniformly sample along the segment of that hit line within the polytope. And you might sample here. And then you choose a random direction, which is this. You identify where it crosses the polytope, and then you uniformly sample in the segment. And this one is guaranteed to uniformly sample in the polytope. It's super explorative. It's very aggressively explorative. I like it because it's not very local, and yeah. But if you want to apply it on our kind of problems, first thing is that we have to make it non-uniform, because we might have a non-uniform energy inside. It turns out it's a straightforward solution is to apply metropolis Hastings adjustment. I haven't seen that before, but it's kind of like straightforward. And then you also need to account when these inequalities are actually not linear, but like non-linear. But I did kind of like a straightforward iterative thing where I use the local linearization that I have to estimate where the line hits the inequalities. Then I, uniform sample and test. And if I'm infeasible, then I re-estimate, these inequalities. So it's really kind of like an iterative re-estimating the first order Taylor of the inequalities to realize hit and run. Here's the pseudocode. We have no chance to look through that, but that is actually the only like new algorithm that I actually proposed in the thing. The rest is just putting together many, many ideas. Oh, sorry, I did these slides back. And to wrap up, this is a large set of methods that you can, with these building blocks put together. Restarts, some slack downhill method, some interior MCMC method. And you have some hyperparameters like how many, you limit the number of downhill steps before you give up and restart. And typically I chose 50. And you might want to allow the interior sampling method some burn-in steps before you actually take samples. But I actually did, the variation showed it didn't pay off. And you might also then take, many interior samples with the interior sampling methods before you restart the whole thing. And I maybe take 10 of those. Anyway, you get the gist of, the huge space of methods that you could have. So I thought, let me test this. I'm later going to apply this and test this in robotics problems and check how well it actually generates nice, diverse solutions to robotics problems. But I first tested it a bit on toy problems. And just to start and get you also on board, like with the intuition, what's happening here is super simple examples. So we have a two-dimensional space. The feasible space is just, this is the full, where I uniformly restart from the full box. And the interior boxes, this is defined by inequalities. If I only do downhill without doing any kind of interior sampling after that, of course, when I only do downhill, I will end up mostly at the boundary of the feasible space. So only doing downhill is bad because you always end up only at the boundary of the feasible space. It's not uniform. It's not correct. That's not the thing. If after you do downhill and you end up at the boundary of the feasible space, you just do a single step of hit and run, just one single step, it's already much better. Yeah, I say here non-linear hit and run, but it's because everything is linear. It's just the same as linear hit and run. Okay. If you do just two steps of hit and run, so downhill and then just 2 steps of hit and run, you actually have really good distribution already in the interior for this box, of course. So this is nice. Okay, a bit as expected. And just as a sanity check as well, I also really checked that the number is very small, but for these tiny problems, and this is a box with some energy defined on it, and the energy is located around, one of the corners. For tiny problems, I could really evaluate also the correctness of the distributions, computing the Earth mover distance. It's super expensive to compute, but for tiny problems, fine to compute. And all of these methods, yeah, they end up with the same distribution. They all minimize the correct. They are all correct. They all sample correctly from the correct stuff. That's just what I want to sanity check. Okay, now the more interesting thing is about how to evaluate diversity, in particular in terms of discovering local optima, because this is where I come from, robotics problems with many local optima. Do these methods actually discover local optima, which means modes in a sampling? And for that, I defined a toy problem, which I call the modes problem, which has like one big central mode, but then many small modes at every corner of a cube. And that cube could be d-dimensional. Here it's just 2-dimensional. Here it's also 2-dimensional. Here it is actually 6-dimensional. So a 6-dimensional cube has already quite a number of corners you can compute. 64. Anyway. Okay, so there's many modes. So first, if you only do downhill, you end up again at the corners. If you do like just 5 steps of interior sampling after that, you end up here. So this is kind of like fine. If you go to higher dimensions, it happens that normal methods, so for instance, if you do uniform restarting, the central mode is so strong that you might very often not end up sampling at all at the corners. So in higher dimensions, you suddenly, lose the quality of really discovering all the modes. And here, doing more clever restarting, like distal restarting, actually helps immensely. Apart from these, properties of the methods, the more interesting question is, how can you put a number to these findings? How can you say this is good and this is not good? How can you assign a metric to all of these algorithms? And that is I find a super interesting problem, actually. So if you would know the ground truth, you could just evaluate the correctness using Earth mover distance, trying to estimate the Kalb-Leibler divergence, something like that. Okay, but that only works for tiny problems, and of course not for problems where you don't know the ground truth, like real robotics problems. And then if you look into the literature, most like sampling methods, I had the feeling they evaluate something like uniform coverage, or so how uniform these points are distributed. For instance, you could for every point look at the k nearest neighbors, say the 10 nearest neighbors, and then check if they are like uniformly close. Like everywhere in the space, the neighbors are approximately 3 millimeters away, right? It's also when you do uniformly sampling on shapes or something like that. In geometry, maybe you have very much also such methods, right? So these are like, I would say these are metrics that look locally around the neighbors. What is the distribution of distances in the neighborhood and stuff like that? And based on that, evaluate how uniform the coverage is or so. But I had and also if you think about Stein variational methods, they have like local kernels and they try to push you away. And so I feel they're all quite like local. The perspective of these metrics is local. And I had an issue of finding a metric that actually tells me, did you also discover a new mode? And after a while, I had the idea to look at the minimum spanning tree of all the samples that I found so far. Okay. Sorry, I'm not sure if you see that, but you shouldn't see that. So the minimum spanning tree of all the samples you found so far, I found this an interesting actually object to characterize the samples that I found. Why is that? So think about this here, like the minimum spanning tree of all of these samples, it has to connect all of these samples. And of course, the minimum spanning tree inside a densely region will have smaller and smaller edges. All of these edges of the minimum spanning tree of all of these points, so will become very small. But then if you look at the minimum spanning tree of all samples, there need to be edges also connecting the modes. So the minimum spanning tree will have at least 4 edges here, which are really large in the limit of taking many samples, and they will remain large also if you take many samples, but all the other edges become very small. That's an interesting property, right? And if you would even identify these exceptionally large edges, they are an indicator for, oh, I discovered the mode. And so and now if you then also sum up the length of all of these edges, it's also an interesting quantity. So if you sum up the linear length of all the edges of piece 1, this is the total length of the minimum spanning tree, then yeah, it just increases. The more samples you get, it increases. And it's interesting. I don't know if there's mathematicians here, but I think that by investigating the limit of what is, of how it increases with having more and more samples, I think it actually tells you what is the dimensionality of that space. And I wish there is a mathematician, or I met a mathematician that can prove that. But I think the law of how the total length of the minimum spanning tree increases with sample of distributions actually tells you how the dimensionality of the sampling space.
Question, Marc.
Yeah.
How would you distinguish between very dense sampling and those long edges if you just look at the bottom line number of the total length? Is it really a telling number?
Well, I haven't explicitly looked, like I have never like explicitly analyzed or distinguished, oh, there's the long edges and there's the small edges, right? I just, visualized them, or like, not visualized, I thought of them like that. And the reason why I find this thought is interesting is actually now the second point that I wanted to make is, if you like square the length of these edges and then sum them up, then intuitively the following should happen, because the squares of all the edges in the dense region, they get close to 0. And if you sum them up and there would be one node, actually the whole sum would actually go to 0, because the square of these very short lengths goes faster to 0 than summing up the many samples, right? But some of these edges, they don't go to 0. These are exactly the edges connecting to the modes. And therefore, I hypothesize, but I didn't do any math about that, that if you sum up the square of all the edge lengths, it actually converges to one constant. And that constant, it's an indicator. It's just the sum of, the squares of all of these mode separating edges. And empirically, that's what I found. That's this lower curve here. Okay, so my answer to the question was, I never explicitly distinguished, the one or the other edges, but I felt that that should be the reason why adding up squares should lead to a very different problem. And that's the case, actually. Okay, and here's the next slide again, evaluating these things. Basically here, once all the modes are covered and found once, then this latter thing, adding up the squares, kind of like reaches very quickly some number, which eventually decreases a bit because, the smaller edges become smaller and smaller, and then converges to that number. And really confirms the profile of first you find the modes, and once they're found, this adding up the squares actually is done. Yeah, and you have the diversity done. Here, it never found the modes, so it actually increases further. But here, with a different, distal restarting method, same thing. You very early on discover all the modes. These are actually quite a lot of modes. And then once you discover that, it basically becomes flats out for this metric. Okay. I just wanted to suggest that this whole minimum spanning tree on the samples is an interesting thing. And I've never seen it before, but I actually really find it interesting to perhaps make statements about modes and stuff. And I wish, mathematicians would more look into that. I didn't. Okay, let me move on a bit to robotics problems. Oh, sorry about that. Oh, I have videos for that. I hope the videos also work. Let me check. Hope you can see.
You see.
It's not a continuous video. It's just, discrete frames. So it's normal if you don't have a high frame rate. These are actually 10 samples from an inverse kinematics problem where the robot is, located at a table, has to reach that gray dot there, and there is like this obstacle here. Simple inverse kinematics problem, and we want to sample from that one, and that's an NLP sampling problem. Here's another one where the inverse kinematics problem is a bit more elaborate. So you want to sample graphs of this funny shape. Yeah, and these are like 10 different, this is an NLP sampler generating 10 different samples from that inverse kinematics problem. And here is one that is more elaborate and was also a core motivation thing for me. Let me just look at it. So what you see here is actually a number of sequences of 1, 2, 3, 4 steps. And this is a sequential manipulation thing. So first push the box, grab the stick, and then with this move the stick to the ball. So this is a sequence of 4 interconnected inverse kinematics problems. I call this keyframe optimization. And this is a core subproblem within TAMP solvers. And I can tell you that this particular one actually has a nasty amount of local optima. And this is one I ran upon when I wanted to solve TAMP problems. And this has tons and tons of local optima because you can push the box aside in many ways so that it is not anymore an obstacle to reach for the stick, and then use the stick to reach for the ball. Also, you can reach the stick, grasp it at this end or at the other end. So some of the samples actually reached for the other end. Maybe, yeah, that one. And you can also push it in many different ways, the box and so forth, right? It's really hard to discover all of these possible ways of how you can do that thing, but it is necessary if the method eventually wants to prove some kind of probabilistic completeness or something like that, if you then do also motion planning. And so this was like really, really a hard problem, and that motivated the whole work. And here are results presented in a manner that is really hard to digest and read for you. But let me first make one statement. I explained, I evaluated all of these different methods. Each of them was not pretty simple. I just pulled together a couple of methods that I had around or so. But in total, it was like almost like 1,600 different method combinations that I tested, because I tested, for downhill, all the possible downhill methods, all the possible interior sampling methods, and different, hyperparameters, how long burn-in time and sampling time and stuff like that. And can I zoom in here? No. If I escape these slides and then would zoom in here, let me zoom in here, maybe. You see that these plots, they have like tons and tons of crosses, and each cross is a particular method. And it has, I'm assigning 2 quality scores to the method. I'm explaining in a second. But each one is actually, each cross is a different method combination. And here there's a little key, which is cryptic to you, but it would tell me what kind of method this was and so forth. But I also, at least to have a larger overview, let me make this again full view. I also colored them, and the coloring actually distinguishes the interior point sampling, the interior MCMC method. And that's an interesting structure. Okay, so to make sense of all of these points, it really required me to look into that a lot, and it was really hard to make systematic variations or something like that. You see. Let me say something about the 2 metrics that you see here. The gist is that the further to the bottom right, top right you are, further top right is better. Why is that? Because this is diversity, and this is the cost of generating samples, the computation cost of generating samples. Inversely, actually. This is basically how many samples do you get per evaluation. And when I say evaluation, I mean the evaluation of F, G, H and their gradients at some point. So this is really, the number of evaluations in optimization would be, I don't know, you need 100 evaluations to find an inverse kinematic solution. Here we ask how many evaluations do you need, or how many samples do you get per evaluation? In the best case, 1. That's like if every evaluation gives you a new sample. But here you need at least 2 evaluations per sample, or I don't know, 5 evaluations per sample, something like that. So you want to be at the top right, and this is the diversity per evaluations. How much minimum spanning tree total distance do you generate diversity with the evaluations? Okay. As I said, it's like really hard to make sense of all of these many results or so, but let me highlight some things. First, for instance, an interesting one is that the green one is actually this hit and run method. And the hit and run method works really well on the box problems, also the modes problems. The green stuff with many different settings, but the interior method is always hit and run. Works really well, and also has the top candidate usually, except for inverse kinematics problems where suddenly another interior sampling method like is systematically better, which is the manifold RT. And that's interesting. And my explanation is that hit and run is really good for inequality dominated problems. So all of these problems, there's lots of inequalities and interior space. Whereas these inverse kinematics problems, they are mostly manifold problems, like where the infeasible space is kind of like a thin manifold. And in that case, it's actually the manifold methods, so both of them can do it, but the manifold methods actually like really perform systematic better. Okay, that's one finding that's sort of easy to read from these graphs. But then other findings, let me just do it here. And I did this manually. It was hard. I don't have like really props, but this is my interpretation of this whole data. So what didn't really pay off actually was the burn-in steps for interior sampling, because the whole stuff is very aggressive. We restart very often, and then spending compute costs for interior sampling, this never paid off. Sorry, for burning time, this never paid off. Also, plane gradient steps actually never paid off. Of course, if you can do Gauss-Newton steps, and we do Gauss-Newton in downhill. Then the downhill reject methods, that's a bit more surprise, like Wolfe, also they didn't really pay off. That's a surprise if you are used in constraint optimization. Nobody does constraint optimization without backtracking and Wolfe conditions. But here, because we restart so often, so aggressively, somehow it didn't really pay off. And also injecting noise during downhill didn't really pay off so much. What paid off was actually this hit and run, especially for inequality dominated methods, and the manifold like interior sampling for equality dominated methods. Okay, looking at the time, let me just, maybe go ahead a bit more quickly. Another finding that I found interesting is that with the restarts, I hoped that doing clever restarts, like distant restarts or I tried different things, would pay off. But actually, especially for the robotics problems, it did not pay off. And when I try to understand and analyze and manually look into the data and why and so forth, I think my understanding now is that in these cases have really many local optima. Yes, they're highly multimodal, but all of these local optima are not spread out in the whole space. These many optima are also very local in some rather narrow space. And that's not what I expected. I always thought if a problem has many local optima, and naively, then they might be spread out all over. Not at all. All these local optima within the robotics problems are also in some quite narrow constrained space. And doing very distal restarting didn't help, really. So that was really some insight in the structure of these problems that I found. Okay. Oh, sorry. This is discussions. I don't have too much time. Maybe actually officially just 2 minutes. Maybe I can use one more. So
that's okay.
One thing I think now there is actually on the conceptual level many interesting discussions. I just pick a few and go over others. One thing is the role of Lagrange parameters. In constraint optimization, Lagrangian theory, KKT conditions is everywhere. Primal dual, everywhere, right? Here, when I'm totally used to these methods and doing dual updates and augmented Lagrangian and everything. And I was always, while doing this work, thinking, can I not use Lagrange methods somewhere, somehow? And in optimization, these Lagrange parameters, of course, they, you could relate them to the KKD. They make a statement about the stationarity at the single optimum, because in optimization, we could converge to one point. And at this point, we have Lagrange parameters, fulfilling KKT conditions. For the sampling, especially for interior sampling, turns out Lagrange parameters don't help because, constraints are never active, basically. Probability of constraints being active is 0 if you sample in the interior. So the whole in interior sampling, no Lagrange parameters, although it is constrained sampling. For manifold sampling, you could think that Lagrange parameters help because, locally at least, they tell you how you can push back to the constrained manifold. That's what KKT kind of like means. But actually, the actual methods that perform well, like manifold marching or like MCMC marching or RT, they always reproject onto the manifold. They make a step, reproject, and that works really well. And also here, I actually never found like a role for Lagrange parameters, which I found interesting. So my point is, just a finding, a curiosity. I didn't find any role of Lagrange parameters in this whole problem, although it is actually constrained about constraint sampling. Another interesting discussion is how does this all relate to diffusion models? I defined a relaxed NLP. You could also think about the diffused NLP. Like we have the distribution P, but you can diffuse that distribution, and it gives you then, and the question is, can you then invert that diffusion to have actually a denoising process to generate sample from the distribution? I looked into that. And bottom line, I'm not going to go into that in the paper. It's a discussion, but it all didn't work out, and it eventually didn't make sense. It was like a super interesting learning and intellectual exercise, but it didn't lead to anything useful. And I'm curious, you can look into it, but it didn't lead to anything useful. Briefly, I also mentioned that my methods are very much sequential methods. You restart, downhill, sample, restart. So single particles always, restart. And you could compare this to population-based methods, and I'm sure you could actually come up maybe with better methods that restart whole populations to go downhill, a bit like Stein variational. I didn't look into that, but I think there might be like huge opportunities to make better methods. And super quick, I think that this whole methodology is gonna be the winner, I hope, also of my research, and will trigger many projects, and I'm planning also for projects to use this methodology to generate data, like to generate diverse data. That's the big gist of why I'm doing all of this, right? To generate good data, like proper model-based optimal data, very diversely. And I think that's kind of like one way to think about the future of robotics. So, and I hope that this NLP sampling methods actually might play quite important role in that. Okay, for the sixth time, I'm a bit over. So my conclusions, I think also even educationally and intellectually, I think it would really be nice to treat optimization and sampling jointly. I think it's really fruitful to try to bring these fields together. And this is one really attempt. This particular problem formulation, is, as I put it there, I find it interesting, and it also leads to open questions. I hope you noticed that. I'm not sure if there's, and let me know if you think that there is other people that formulated the problem slightly differently or so. Even asking, how you best formulate the problem is interesting. And then I said this already, I hope that these methodologies could have really impact like in the future of how you do actually robotics and combine database learning methods with model-based data generators. That's it. Thank you.